Okay, in section 3.4, we're going to be looking at graphs of polynomials and some specific characteristics of these graphs. And let's start by looking at the graph of y equals negative times x plus 4 times x minus 1 squared. Now notice, if we tried to figure out the degree of this polynomial, so if I was to expand this, this guy here would give me an x squared term. This would be an x term, and x times x squared is going to give me an x cubed, which is a degree 3. My leading coefficient is -1. So that means that my graph would be starting in quadrant 2, in quadrant 4. Now, the key part is the zeros. What value makes x plus 4 0? Well, that value, of course, is -4. And notice that is right there on the graph. And the value that makes x minus 1 0 is going to be when x is 1, and that value is right there on the graph. Now notice the graph behaves differently at -4 and differently at 1. And if we look at the factors in the equation, okay, x plus 4 has an exponent of 1, x minus 1 has an exponent of 2. So these exponents are called the multiplicities. If the multiplicity is 1, then the graph passes straight through the 0 of that factor. If the multiplicity is 2, then the graph comes up and forms a parabola at that 0 of the factor. If we take a look at this next one, again, if I was to expand x minus 3 all cubed, that would give me an x cubed. X plus 4 is an x. If I multiply those, I'll get degree 4. My leading coefficient is 1/9. So therefore, this thing is an even degree leading coefficient positive, starts in 2, ends in 1. Again, if we look at the zeros, the first 0, -4, passes straight through. The exponent is 1, the multiplicity is 1. Here, the 0 is that 0 is 3. And notice at a cubic, the graph forms a bump and squiggle. I call it a bump and squiggle. The book refers to it as tangent and then crosses at x equals 3. So we have 3 multiplicities that we have to deal with. A multiplicity of 1, the graph passes straight through the 0, okay? If there's a multiplicity of 2, so say, for example, we have x minus 2 squared, the 0 would be 2. If the degree is 2 or even 4, 6, or 8, the graph will form a parabola at that 0. Finally, if the graph is cubic, or it should say 5, 7, or 9, an odd degree higher than 1, like 3, 5, 7, or 9, the graph will form a bump and squiggle at the 0. So that's a multiplicity of 3. So to review, multiplicity of 1 goes straight through, multiplicity of 2 is a parabola, multiplicity of 3 is a bump and a squiggle. Now, let's say we want to, for the following, find the least possible degree. Well, if we look at the graph, I have a degree 1, degree 1, degree 1. So that means that my least possible degree for this one is degree 3. Now, as far as the sign of the leading coefficient for question B, well, because this starts in 3 and ends in 1, I know that my leading coefficient has to be positive, and we'll find that leading coefficient later on in part E. Part C wants us to list the x-intercepts, the factors, and the least degree. Well, the first 0 is x equals -4, so its factor would be x plus 4, and the multiplicity is 1. The next 0 would be x equals -2. Factor is x plus 2, multiplicity of 1. The third 0 is x equals 2, which is x minus 2, and a multiplicity of 1. Notice the multiplicities add up to the degree. Question D says intervals where the graph is negative and intervals where it's positive. Well, where it's negative is where it's above the x-axis. So from -4 all the way to -2, it is above the x-axis, and the union when x is greater than 2. So that's where the function is positive. Okay, for D, the function is negative when the graph is below the x-axis, and that goes from -2 all the way up to +2. All right, for the last question, or the last part question, part E, they want us to find the equation of the polynomial, including the leading coefficient. So find the equation. It's going to be y equals a. Now I'm going to list all of my factors with their multiplicities. So x plus 4, x plus 2, and x minus 2. Now, to figure out the value of a, we have to go to our graph and find another coordinate on the graph that is not the zeros. And we can look at the y-intercept. And the y-intercept here is 0 and negative 18. So if I put in negative 18 in for y, when x is 0, that will allow me to figure out the value of a. So I get negative 18 is equal to 4 times 2 is 8, and 8 times negative 2 is going to be negative 32. And I still have to multiply it by the a out front. Then if I divide both sides by negative 32, and now I can reduce this because the negatives become positive. 2 goes into 2 goes into 18 9 times, and into 32 16 times. So finally, my final equation, I'm just going to get rid of the a here, and I'm going to replace it with 9 over 16. So there would be the equation of this graph. Okay, let's try another one. So this one here, we start with the degree, multiplicity of 1, multiplicity of 1, multiplicity of 2. So the least degree is going to be 4. Sign of the leading coefficient, well, because this thing starts in quadrant 3 and ends in quadrant 4, the leading coefficient will be negative. And again, we'll find that in section E. For C, the x-intercepts, the factors in the least degree. While negative 5 is the intercept, x plus 5 is the factor with a degree 1. X equals negative 1 is the 0. X plus 1 is the factor, degree 1. X equals 4 is the 0. X minus 4 is the factor, and degree 2 because it's a parabola. So for part D, they want to figure out where is the graph function positive and where is the function negative. Well, it's positive when the graph's above the x-axis, so from negative 5 to negative 1. So negative 5 less than x less than negative 1. And where is it negative? Well, from when x is less than negative 5, union with negative 1 to 4, union with when x is greater than 4. So notice we excluded 4 here by writing it the way we did here, because at 4 it actually equals 0, and we want to know where it's greater than or less than 0. Now for part E, to find the equation, again, y equals a is my leading coefficient, and I list my factors, which are going to be x plus 5, x plus 1, and x minus 4 all squared. Again, I'm going to take my y-intercept, is probably the easiest, and the y-intercept in this particular case is 0 and negative 80. So I'm going to put a negative 80 in for y when x is 0. So this is going to leave me with 5, 1, and negative 4 squared is 16. So 16 times 5 is going to give me positive 80. So if I divide, I get a is negative 1. So therefore, in my equation, all I need to do is put a negative here because a is negative 1. Okay. There are a few questions that you can try on page 147 of your textbook. And basically, those questions there, all they're getting you to do is practice by finding the zeros given a polynomial in factored form for 1 and 2. And again, they want you to do some other stuff for 3, 4, and 5, very similar to what we did in our examples. Okay? All right, when you're done that, I'm going to continue with the video here. Okay, and second part, so this is the second part of 3.4. So now we want to sketch this polynomial, okay, and identify all the information in the question. So we know what's the degree? Well, I have x cubed times an x, so my degree is going to be 4. The leading coefficient is negative. So a negative 4 we know starts in 3 and ends at 4. The zeros, well, the value to the first zero, the zero is negative 2. So for D, it's x equals negative 2 with a multiplicity of 3. And x minus 4 has a zero of x equals 4 with a multiplicity of 1. The y-intercept, well, for part E, to find the y-intercept, I let x equal 0. So I have y equals 0 plus 2 cubed and 0 minus 4. So 2 cubed is 8 times negative 4 is negative 32 times a negative up front means that my y-intercept is going to be positive 32. Okay? So for part F, to find where the intervals are positive and negative, we'll deal with that after we draw the picture. So let's draw our picture. And again, this is just a rough sketch. Okay? So on our sketch, we know that I have a 0 at negative 2. I know that I have a 0 at 4. Okay? And I know I have a y-intercept at 32. I know the graph starts down in quadrant 3, and the multiplicity at negative 2 is 3. So when it comes up, it's going to form a bump and squiggle. It's going to take off to here, and somewhere between the y-intercept and 4, it's going to have to turn around. And then it comes straight through 4 because the multiplicity is 1 and heads down the bottom direction. Now, part F, to figure out where the graph is positive, it's going to be from negative 2, 4. And to figure out where the graph is negative, it's going to be when x is less than negative 2 and when x is greater than 4. Okay, now the only difference with question 4 compared to the last one is we have to do synthetic division so that we can factor this. Okay, so we can look at the first parts of this question, and then we'll get to the synthetic division when we factor this. So if we start with the degree is 3, the leading coefficient we know is negative 2, and the end behavior, well, it's an odd degree with a negative leading coefficient, starts in 2 and 4. The y-intercept is the constant, and parts D and F we'll figure out after we do synthetic division. So again, for synthetic division, we're going to choose factors of the constant, plus or minus 1, plus or minus 2, or plus or minus 4. We'll start with 1. So y of 1 is going to be negative 2 times 1 cubed plus 6 times 1 minus 4. This equals 0. So therefore, we know that x minus 1 is our first factor. So now we'll do our step. Again, synthetic division, negative 2. There's no x squared term, so you got to put a 0 in there. This drops down. I get 0, which is perfect. So the original factor was x minus 1, and negative 2 minus 2 plus 4 become the coefficients for my next factor, which is 1 degree less than a cube. So it's negative 2x squared minus 2x plus 4. And then I'm going to factor a negative 2 out of that and bring it out front. And then this trinomial is going to factor into negative 2x minus 1. That's going to be x plus 2 times x minus 1. And notice I have 2x minus 1s. So if I write those together, x minus 1 times x minus 1 is x minus 1 squared times x plus 2. So this equation is the same thing as this equation, it's just in factored form. So now the zeros are going to be 1, because 1 makes this guy 0, and it has a multiplicity of 2. And our other 0 is going to be negative 2, and it has a multiplicity of 1. So if we sketch this graph now, we'll start with our zeros. I have a 0 at negative 2. I have a 0 at plus 1. Okay, and I have a y-intercept at negative 4. I know the graph starts up here and it ends down here. And I know the multiplicity at negative 2 is 1, so it's going to come down. And then somewhere between negative 2 and 1, it changes direction. And we'll figure that out in calculus. It goes up. Multiplicity is 2, so it's tangent, and it heads down in that direction. Now, to answer the last part, where is it positive and negative, which was part F. So F, the graph is positive when x is less than negative 2. And the graph is negative between negative 2 and 1, and when x is greater than 1. So I'll put a union symbol in there. Okay? All right. I want you to pause the video and give this guy a try. Okay? Okay, hopefully you've had a chance to try this one. Okay? And again, looking at the factored form, this is a degree 1 out here. So an x times an x cubed, the degree is 4. The leading coefficient is 1. So we know that it starts in 2, ends in 1. The zeros, first 0 is x equals 2 with a multiplicity of 3. X equals negative 1 with a multiplicity of 1. To figure out the y-intercept, all you really have to do is cube the negative 2 and times it by 1. The y-intercept is going to end up being negative 8. And for the other part, F, we'll figure out after we draw the sketch. Again, I have a 0 at 2 and a 0 at negative 1. I have a y-intercept of negative 8. You know the graph starts there and ends here. So it comes down to negative 1 where the multiplicity is 3. It's a bump in the squiggle. Then it's got to come down through 8, negative 8, turn around, and come back up through 2. Because the multiplicity is 1, the graph goes straight through there. All right. Now, the last thing we're going to talk about is transformations in regards to polynomials, and they're the exact same as they are for all of our other graphs. So let's take a look at the graph y equals x cubed and sketch the transformation. So to start with, let's start with the basic points for y equals x cubed. And I'm going to use 5 basic points going from negative 2 to 2. Negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. And remember, our x cubed graph looks like that with a bump and squiggle at 0, 0. Okay? Now, I'm actually going to convert these over here to give myself more room. Okay, now looking back at our equation, I have a is negative 2. Oops. A equals negative 2. B is equal to 4. X or H is equal to 1. And K was equal to 3. So my mapping notation is going to be x over 4 plus 1 and negative 2 times y plus 3. So generating my new table. The y values are fairly easy because there's no fractions involved. Negative 8 times negative 2 plus 3 is going to be 19. Negative 1 times negative 2 plus 3 is going to be 5. Negative 2, or 0 times negative 2 plus 3 is 3. 1, and the last one's going to be negative 13. Now, placing these in here, I'm going to get a few fractions to deal with. Negative 2 over 4 is negative 1/2. And negative 1/2 plus 1 is going to be 1/2. Negative 1 over 4 is negative 1/4 plus 1 is 3/4. 0 over 4 plus 1 is 1. 1 over 4 is plus 1 is 5/4, and 2 over 4 plus 1 is 3.5. So if I was to sketch this graph, okay, and it won't all fit on the one here, but we'll try it. So 1/2, let's start with the bump and squiggle point is at 1 and 3. How do I know that's my bump and squiggle point? Because it corresponds to the point 0, 0, which is the bump and squiggle point for the original graph. 5/4 and 1 is 1 1/4, and 1 is right about there. The next point is 3, 1.5, and negative 13. So 1.5 and negative 13 is going to be way down here at the bottom. And then if I go back to the next one, 3/4 and 5. So 3/4 and 5 is here. And the last one is 1/2 and 19, which is going to be way up here. So this graph is going to be hard to draw in this small grid, but there's a little bump and squiggle there, and it continues down. Okay, so if we graph this and we stretch out our horizontal axes, we get a more bump and squiggle, but the bump and squiggle point is right there. Okay, and you can see there's the original graph. The blue graph's a better grid, is y equals x cubed, and there is the transform graph. You can see it's very narrow because it's stretched vertically. Okay, last question is dealing with an application, and it says Bill is preparing to make an ice sculpture. He has a block of ice that is 3 feet by 4 feet by 5 feet. He wants to reduce the size of the block of ice by removing the same amount from all 3 dimensions, and he wants to reduce the volume to 24. Write a polynomial for this situation. Okay, well, I know originally my sides are 3, 4, and 5, but he wants to remove the same amount from each side. So let's take off x from each side. And the volume of the remaining block is going to be 24. So 3 minus x times 4 minus x times 5 minus x is equal to 24. If I'm to FOIL those two out and collect like terms, I'm going to get 12 minus 7x plus x squared times 5 minus x equals 24. And now, and I'll let you do the math, if you were to multiply these out and bring the 24 over and set it equal to 0, you're going to end up getting a polynomial that is x cubed minus 12x squared plus 47x minus 36. So that's going to be our polynomial. Okay, so there's a polynomial that represents a situation. Question B says, how much should he remove from each dimension? So now we're going to factor this polynomial to see what x should be. And to factor that, we are going to use the factor theorem. So I'm going to try putting 1 into the original polynomial. And if I do, I get 1 minus 12 plus 47 minus 36, which equals 0. So therefore, x minus 1 is my first factor. So if I do my synthetic division, going from my polynomial, I have 1, negative 12, 47, and negative 36. The 1 drops down. So therefore, my polynomial p of x is going to be my first factor, which was x minus 1. That's the one we found here. And then this guy is going to be 1 degree less, so it's going to be x squared minus 11x plus 36. Okay, and this is prime, so the only solution is going to be here when x is 1. So therefore, Bill needs to cut 1 foot off each dimension. Okay, so that was kind of a neat application question for polynomials. Okay, there is your assignment for today on page 149. There is the review for your chapter 3 exam. Okay, good luck, and if you have any questions, we can look at those in class.